Now consider this interval. Consider in equals, let in equals closed interval 0, 1 by n. Closed interval 0, 1 by n. Then for all n following, then intersection with respect to n ranges from 1 to infinity n is single term set of 0. In is closed interval 0, 1 by n, then intersection n ranges from 1 to infinity n equals 0. How to prove this one? So here, by the definition of in equals closed interval 0, 1 by n. Then what is I1? I1 equals closed to 0, 1. What is I2? I2 equals closed to 0, 1 by 2. What is I3? I3 is closed to 0, 1 by 3. Etc. What is IK? IK is closed to 0, 1 by k. So in all of these sequences there exists an element 0 itself. So clearly from here we can conclude that 0 fall in intersection n ranges from 1 to infinity I. 0 fall in I1, 0 fall in I2, etc. 0 fall in IK. That means 0 fall in in for all n fall in n. 0 fall in in for all n fall in n. That means 0 fall in intersection n ranges from 1 to infinity in. Okay. Then, but in contains only non-negative numbers. No negative numbers are there. Why? Because it's of the form 0, 1 by n. So in consists of non-negative numbers, means in consists of only non-negative numbers for all n fall in n. Then, since in consists of non-negative numbers, only non-negative numbers for all n, clearly this intersection in contains intersection in with respect to n. Intersection in contains only non-negative numbers. Okay. Now contains only non-negative numbers. Now let x is positive. Consider x greater than 0. Then by the corollary of Archimedean property, there exists nx fall in n. There exists a natural number n epsilon or nx such that 0 less than 1 by nx strictly less than x. This is clear from the corollary of Archimedean property. We already proved this property. Okay. So clearly there exists a positive real number, then there exists a natural number nx such that then 0 less than 1 by nx strictly less than x. 0 less than 1 by nx strictly less than x, that means clearly this x is outside of this in. Why? Because in equals closed interval 0, 1 by n, x greater than 0 and x greater than 1 by nx, where nx is a natural number. Therefore, clearly x is outside of in for all n falling in. X is outside of in means x is outside of intersection in for all n falling in, where n ranges from 1 to infinity. Now here, intersection in consists of 0 elements, but intersection in consists of no number greater than 0. Since x greater than 0 as by the choice of x, and we prove that this x is outside of this intersection in, means intersection in consists of the element 0, but intersection in consists of no positive real number, no positive real number. Also by the choice of this in, it consists of only non-negative real number. So from here, clearly this intersection in consists of only one element, that is 0 itself. Therefore, intersection n ranges from 1 to infinity in is singleton set of 0. Okay. Now listen. Suppose this is in this way. Suppose in equals open interval 0, 1 by n. What happens here? Then what is intersection in? This is our next question. If it is closed interval 0, 1 by n, then we know that intersection in consists of only one element, it is 0. That we see. Now if in is closed interval 0, 1 by n, our question is, what about the infinite intersection? Intersection ranges from 1 to infinity, in becomes what? So far, here what is I1? Open interval 0, 1. I2, open interval 0, 1 by 2. I3, open interval 0, 1 by 3. Ik, open interval 0, 1 by k. Clearly, 0 is outside of in for all n following n. Therefore, 0 is outside of intersection n ranges from 1 to infinity in. Okay. 0 does not consist of 3. Clear? Again, by the choice of in consists of only non-negative terms. It does not contain negative terms. In consists of only non-negative terms. Again, by the same argument, you can choose a real number x greater than 0. Then by the corollary of Archimedean property, there exists nx for n such that 0 less than 1 by nx less than x. Clearly, x is outside of in. For all n means x is outside of intersection in. Therefore, x is, so there is no number in intersection in. Means intersection in does not consist of negative number. Intersection in does not consist of a positive real number. And intersection in does not consist of this 0. Means, so this intersection in is empty. If in is open interval 0, 1, then our answer is intersection n ranges from 1 to infinity in is empty. So there is a difference. If in is closed interval 0, 1 by n, then intersection in consists of only 0, only the element is 0. And if it is the open interval 0, 1 by n, then intersection n ranges from 1 to infinity, in is empty. Agreed. So this is the this is regard these two results. These two results are depends upon the Archimedean property, and the corollary of that Archimedean property is important. Okay. Now there is the what is the countability of a set? We know that set of rational numbers is countable. If there exists a 1-to-1 correspondence with the set of natural numbers, then the given set is a countable set. What about the closed interval 0, 1? The closed interval 0, 1 is uncountable. It is uncountable. Closed interval 0, 1 is uncountable. How? So, this is a well-known result. Closed interval 0, 1. What is closed interval 0, 1? Set of all x such that x ranges from 0 to 1, which is uncountable. Okay. So, how to prove this one? We have, suppose closed interval 0, 1 equals, consider the proof. Set x1, x2, x3, etc. Suppose it is uncountable. What happens? Suppose 0, 1 is countable. Suppose 0, 1 is countable, then closed 0, 1 can be x is set of all x1, x2, x3, etc. Then every xi following this I in the given number, every xi following I has a decimal representation, that is x1 equals 0.b11, b12, b13, etc. What is x2? x2 equals 0.b21, b22, b23, etc. Then what is xk? xk equals 0.bk1, bk2, bk3, etc. Then let y fall in R. Let y is a real number such that this y has the representation y equals 0.y11, y12, y13, etc. such that this y11 differs from b11. You can choose y in such a way that y11 differs from b11, y22 differs from b22, y33 differs from b33, etc. Then clearly yn differs from bnn. That means this y differs from x1, y differs from x2, y differs from x3, etc. That means that's a contradiction. Why? Because there exist infinitely many elements, therefore clearly closed 0, 1 is uncountable. Okay. Closed 0, 1 is uncountable, then set of reals is also uncountable. Why? Because closed 0, 1 is a part of R. Closed 0, 1 is a subset of R. Since clause 01 is uncountable, surely R is uncountable. If R is countable, then it has a uncountable set. That's a contradiction. That's absurd. Therefore, clause 01 is a part of, since clause 01 is a part of R is uncountable. What is set of irrationals? Set of rationals is countable. Set of irrational means complement of as Q in R. So set of irrationals. So set of irrationals is also uncountable. Why? Set of rationals is countable. If set of irrational is also countable, what happens? If set of irrationals is countable, means we have, what is R? R equals Q union complement of R in Q. Sorry, complement of Q in R. Okay, Q union Q complement. That means R equals Q union Q complement. When Q complement is countable, what happens? The Q, we know that Q is countable. Q complement also countable. Union of two countable set is countable. Hence R is countable. But from here we say that R is uncountable. Thus we know that Q complement is uncountable. Therefore, set of irrational numbers is also uncountable. Okay. So our first module is over here. Now let us discuss about the second module, sequence and series, in next class. Okay, thank you.